Let's take a look now at application of these different approaches in multiple regression. The hierarchical approach, actually, I won't demonstrate for you. That'll actually come up a little bit later when we talk about dummy coding. But for right now, let's take a look at the statistical approaches, the backward, the forward, and the stepwise. So now we're on page 109 of the reader, and you can see the syntax here on 109. And the difference between this run and the run prior, where we had all four predictors in the model, so we have year since PhD, number of publications, sex, and number of citations, is this keyword backwards. So in going back a couple pages, that keyword there is for enter. It will actually say enter for the forced entry approach, but now it says backward. And so let's see what this, so basically all four of these predictors are going to go into the model, and then we're going to see if any of them get removed. So here you go, and you can see two models were generated. Basically, the first model has all four variables in, and then one of the variables was removed, number of publications, because it failed to meet the probability of F to remove. So this thing wasn't significant at 0.05, so it gets removed. Let's go ahead and take a look at the next page of the output. You can see the model results here. Model 1, the multiple R was 0.701. The R square was 0.49. And, again, over here, the change statistics for that first model, we don't really do much with it. The null model to adding four variables, it's 0.49, and that's highly significant. But what's interesting is for model 2, now we have a multiple R of 0.693, and the R square is 0.48. So we actually lost about, it looks like about 1.1% of the variance if I take the R square. And here we can actually see, or not even 1.1, but it's about 1% of the variance right on. You can see this is where the R square change comes into work now too. So we lost about 1% or 0.01 on the R square. The change in R square from 0.491 to the current one for model 2, that change was in fact non-significant. And which is kind of what we want to see with this procedure. We actually want non-significance, which is something you're not used to probably evaluating. Don't we want things significant? In this case, we don't. If the backward approach is working the way it should, what's going to happen is that this change in R square is going to be non-significant. Now, what does that mean? It means that the amount of variance that one predictor variable was contributing to the model is non-significant. And that's what again, with the backward approach, what it's doing is it's removing variables that really don't have any importance at all. And it's not really, and by removing those variables, is that going to be detrimental to the overall model? And the answer is no, it's not contributing a significant amount of R square, so it's fine, we can go ahead and remove it. So that's the idea behind interpreting the R squared change, especially when you get 2 or 3 or 4 models. The ANOVA summary tables are right there. For model 1, all 4 predictors, there is a linear association between the predictors and the outcome variable. Model number 2 only has 3 predictors in it. Same thing. We have a significant linear association between our 3 predictors and the criterion. Okay. And then down here we have our coefficients, and you can see the coefficients for model 1. All of these are going to match what we saw in the forced entry because all 4 variables are in the model. Model 2 has now removed one of the variables. It removed number of publications. So removing that, how does that end up changing our model results? And you can see that in this case, year since PhD is now worth $380, when before it was worth $293. This idea of sex or gender, instead of negative 2945, it's negative 2629. And then how much is it worth, the number of times you are referenced in the Social Science Citation Index, it's now 1126 as opposed to 1145. We can do an evaluation as well in the second model, which is kind of the one we want to focus on. And you can see all the predictors are significant. The one that's the most significant is going to be, not most significant, the one that's the most important based on the betas is this one with the value of 0.452, followed by the number of citations, followed by sex. All right, so that's the forced entry approach. Excuse me, that is the backward approach. I apologize, that is the backward approach. So let's take a look at the forward approach, okay, the forward approach, and that's going to be here on page 111. Forward approach, the keyword change is going to be this thing here says forward. And then all four variables, predictors are put in the model. And you can see three models are generated: year since PhD, number of citations, and then sex. So that's the order of entry. Year since PhD is the one it enters first with the highest simple or Pearson correlation, followed by number of citations, followed by sex, having to deal with the significance of their partial correlations. The last variable, which is number of sex, it's which one is left out? Oh, number of publications. So number of publications never made it in. So those three make it in, but number of publications doesn't. All right. You can see we have three models here. Now here we want and here you can see the growth in the multiple R and R square. We go from 0.618 to 0.667 to 0.693. And you can see the R square associated with that as well. And then we have the R squared change statistics. And again, the null model to a model with one predictor goes to 3.82. And the rest of these, now here in the forward approach, we want all these to be significant. And they are. Why? Because every predictor in the forward approach that we want to be allowed to enter the model needs to be significant. So the model number 2, that addition of that one variable, which is going to be number of citations, that contributes 6% above and beyond what went on in the first model. And then the third model, the addition of sex, that is contributing another 3.5% of the variance, and that is highly significant as well. We have three ANOVA summary table sets of results for the three models. All of them are significant, indicating linear association between the predictors and the criterion. And then we have coefficients down below and for the three models. And you can see how things change going from just having year since PhD by itself in the model to adding two more variables. Year since PhD started off being worth $520. But these other variables that enter the model actually have some variance overlap. So what's going to happen is year since PhD, that value is going to start going down. 0.411, I'm sorry, $411, and then $380. So it goes down. Why is it going down? Because these other variables that enter have some overlap with year since PhD. So it kind of takes away a little bit of the oomph of year since PhD. And so that's how that kind of works. Same thing though, you want to evaluate the betas. Typically, forward or backward, you're gonna focus more on the final model that's generated. Here we have three models generated, so we're gonna focus on the third. You do report some of the initial model results, and I'll get to that another time. You have, but the best predictor here is based on the beta, 0.452, is year since PhD, followed by number of citations in the Social Science Citation Index, followed by sex, all right? And we have significance values, everything's significant, and there are zero orders and the partial and the semi-partials, which I'll talk about another time. And then finally, on page 113, we have the stepwise approach, which you can see here, stepwise, year since PhD, number of publications, da, da, da. So it's doing the same thing. I actually changed the default values here to 0.10 and 0.15 just to see if I can get things to work any better. They really didn't, but that's how you edit that. But for you guys' homework, leave everything as it is. Don't change the defaults. Here you can see it ends up four variables are dumped or added to the model one after another, including number of publications. Why did number of publications come in at this time? Because I changed the default, so I made this technique a little more lenient, and there are times or reasons why you would do that. But again, for your purposes, for this class, you're not going to do that at all. The essentially, the stepwise, the forward method kicks in first, and then the backward starts doing evaluations. However, nothing got kicked out. So essentially, this almost looks like a forward type of design where you have four different models, and at each model, for each model, a new variable has entered. So it's kind of uninteresting because I couldn't really, one of these days I'll work up an example where the backward will kick out something. I just don't have one yet. And but you can see that we end up generating four different models. And here we want to make sure, because this is more the forward approach, we keep adding variables. So we want to make sure all these things are significant. And in that last variable added in, predictor only accounts for 1% of the variance, but the significance value, to allow it to get in, I'd made this really, really generous. So this came in even though it's at 0.087. All right, so again, not the best example, but it's okay. And then you have your ANOVA, your model results up here, linear association between the predictors and the criterion. And then you have your coefficients, which are interpreted in the standard, in the typical way anyway. And because this is a statistical approach, the stepwise approach, we're going to focus more on what's going on with model number 4, because that's kind of our endpoint. And that's a real quickie on backward, forward, and stepwise having to deal with multiple regression. All right, I'll start backfilling even more over the weekend here. Lots of other little videos coming. I want to make sure you have everything you need to do the homework, which I think is due next Friday. All right, thanks, gang.